So the second part of these supermassive binary black hole mergers that I want to discuss today is the imprint of spin flips and gravitational recoil, basically. So since a breakthrough study in 2007, we know that often gravitational, due to asymmetric gravitational wave emission, black holes can receive very large kicks, which are also often accompanied by significant spin flips that have been, for example, also shown in the so-called spin flip mechanism. There's even an observation of a radiola of a quasar, which is 3C186, that was measured, where a very loud source was measured offset from the mass center of the host galaxy, and also very high blue shift was observed in the broadline emission region. So that's a pretty good candidate for a recoiling black hole. So motivated by these findings, we wanted to investigate which impact the precession of the black holes while they in spiral and merge would have on electromagnetic features from the system. So the system we chose to investigate is actually shown, for example, on the right plot over there, where I'm plotting the Z component of the individual spins of the two black holes. I also have a little movie on the left of the spin precession exactly of one of the black holes. So as you can see, and the evolution progresses, the two spins start initially within the plane, but as they interact with each other, they precess upward and start having a larger component that basically is aligned with the disk orbital angular momentum. And afterwards, getting close to merger, the spin points within the plane again and kind of shuts off right before merger. So that's the interesting precessing case that we basically want to investigate. Just a brief note on how we perform, or how we do that. We do full 3D GRMHD simulations with the so-called handoff procedure. So the circumbinary disk beforehand is equilibrated for around more than 150 orbits, and with a cavity cut out basically in the center, and this data is then basically interpolated on a grid that is evolving to the black holes together with the circumbinary disk in full 3D. We use the Illinois GRMHD code for that, and an analytic prescription for the spacetime, which are basically superposed Kerr-Shield coordinates. And the video that you see there is actually a video from the simulation. Just to appreciate maybe the difference between what precession is doing to the system, I've here plotted two snapshots in the equatorial plane at around 2,500 m after handoff, and you can see that the tilts of the spins create very interesting dynamics near the black holes and basically tilt the mini disks with the spins. You can see that on the left, which is the actual simulation, and on the right you see the two mini disks, how they would look like if the spins would be only aligned but would have the same magnitude, pointing basically aligned with the disk angular momentum. So now let's look at the movie here that shows the system basically in the XZ plane and the outflows that the precession of the spins is generating while the two black holes are inspiring. So opposed to maybe other simulations that have a line spin, the precessing spin case doesn't show a coherent jet outflow as the black holes are precessing very fast, and a lot of matter is dynamically ejected and interfering basically the accretion streams. However, there's a period of stronger activity which exactly coincides with the time when the spins have a significant Z component pointing outside of the disk, and you could see that in the movie, basically at a certain period of time. To appreciate that, for example, a little bit more, this is how the mini disks basically look like during a time when the spins point upward. So this is a time where actually something like a intermittent jet is being developed, especially for one of the black holes that you can see here, and the mini disks are tilted here with respect to the orbital plane. To quantify that a little bit more, I said that we basically observed the specific time period where the spin precession of the black holes causes the jets to be stronger and propagate outward. And this period of time is exactly correlated with this alignment. So what you can see here on the top 3 panels is basically a time average over the initial period when the spins are mainly pointing within the orbital plane. Then it's a time average over the period of time that I consider when the spins have a significant component pointing outside of the disk. And then the last period just before merger when the spins are roughly within the plane again. And it's the magnetization that I'm showing there, and you can see that it's enhanced within that period of time. In the lower panel, you can see the corresponding pointing luminosity measured for the close to the horizon for the 2 different black holes, and also at the cavity edge, which is basically 20 m or roughly the separation of the 2 black holes at the upper hemisphere of the 2 black holes. And you can see that exactly during that period of time, the pointing luminosity is strongly enhanced, and also, so that's the green curve, but also it seems to come mainly from a single black hole. The other black hole doesn't really form a coherent or strong outflow. Yeah. So, and finally, I also measured the pointing luminosity at a large distance from the source because the system is very dynamical, and there's a lot of mass pollution, as you might have seen in the initial movie that I've shown. It's not so clear whether that luminosity created at small distances close to the black holes will actually be able to propagate out and create a strong pointing flux. But measuring at the pointing luminosity at 200 m, we can see that this feature basically survives, which I'm kind of trying to show within the 2 red lines over there. So that basically shows that the pointing luminosity is enhanced in that period of time when the 2 black holes precess out of the plane. Okay, so just the summary. We've performed 3D full GRMHD simulations with equilibrated circumbinary accretion disk and studied the impact of precessing spins on the electromagnetic luminosity from that system. What we've observed is that there is a characteristic time period when the precession of the black holes causes the spins to point upward, such that the emission through jets is enhanced, and that could potentially be a multi-messenger signal for such a merging binary. We also observe imprints of the CBD accretion on the electromagnetic luminosity, which I haven't talked so much about, but obviously the feeding mechanism onto the black holes will be fundamental in how much flux can actually be stuck onto the black hole that eventually leads to the jet emission. Thank you.
Okay, we have time for questions. Do we have one in the back? Or maybe just this one up here in the front. Come up to the mic with your questions. And I guess I'll ask the first one. I think we can see it still here. Well, do you have a feeling for why this big difference between black hole 1 and black hole 2? Like if they're both, is it just a fluke of that's where the gas is at the time, or?
Yeah, I think that's the main reason, because the black hole locations with respect to the m=1 mode of the circumbinary list will impact how much flux and mass can basically being accreted on one of the black holes, together with the spins being within the plane and potentially targeting even the other accretion disk. I think that can lead to like this nonlinear dynamics where one of the black holes is just prevented from accreting enough in order to form a second jet. So I think in principle we can test that by positioning the black holes at different locations or running the simulations at a larger separation and see whether both black holes show some sort of symmetry in how they create these jets.
I can just run the mic if it's really awkward.
Hey, great talk. I had a question about the mini disks that form around the black holes. Do the disks have enough time to align with the black hole spin? Do you expect that to have any significant change in the electromagnetic signal we might see from those mini disks compared to a non-spinning?
That's a good question. So I think I'm not sure if I can really call these features that we see there. I've called them mini disks, but I'm not sure if how disk-like they actually are compared to the mini disks that form with black holes where the spins are aligned. Because I think to a large extent, as you can see here, maybe in the left plot in the XY plane, these are just streams that get aligned with with basically the spin direction of one of the black holes. So and because the precession timescale is so fast, I think that I think there's very little time to actually form matter actually to maybe orbit the black hole maybe more than one time. But I have to look into this in detail. Great question. Excuse me?
Maybe larger separations.
Oh yeah, yeah. Then for sure, larger separations would extend the precession timescales, and then there would be more time. Yeah.
Thank you.
Can you just go to the mic so that the people online hear?
You show the light curves again. See different one, but there are several high frequency oscillations and some lower frequency ones. Can you tell us which one is which? What are they? And there's a period of 5,000 kind of, from 5,000 to 10,000, but in there are some high frequency oscillations. So is that an orbital? Is that a precession? It's easier in the m dot, but the light curve too.
Yeah, that's a good question. So I think at that point, I don't understand all of those features. I think this, this dip here in the EM luminosity is related to the outer accretion stream. Basically, that if you look at the very top plot, I'm measuring there the mass within the cavity and also the mass of the individual black holes. So there you can see that this feature pretty much correlates with the mass that's being fed onto the black hole, and this mass declines, which also would remove flux being transported to the black hole, such that also the EM luminosity would decrease. Then those features at a higher frequency, I think, are most likely related to variability in the accretion rate itself. But
What is the orbital period?
Around 400 M. So I think, they might be well related to the refilling cycles of the individual mini disks. But it's hard, But they're on a shorter time scale, so.
Okay. All right. Thank you, Rishi, again.
Hi, so I'll be talking about GRMHD simulations and also some ray tracing studies we've been doing, massive binary black hole simulations that are accreting gas that heats up, dissipates, turns this free energy into light. We try to do this from end to end so we get very accurate, kind of self-consistent electromagnetic predictions of these LISA counterparts. I'll be talking about 3 different projects that are led by 3 different people. Lorenzo Inaghi, who graduated and is now a staff scientist in Italy at a supercomputing center. Minja Kim, who will be joining the grad student population at UPenn this fall. He's led this leakage project. Lorenzo led our first simulations of mergers, and then Kitty Porter, who's also graduating and going to UVA for a postdoc. So I'm going to back up a little bit in kind of the campaign of our larger collaboration. So these are the first, from in spiral, from relaxed initial conditions, simulations of binary black holes in these gaseous environments with MHD that then eventually merge, and then the evolution is followed in a post-merger phase. So we get all epochs of evolution, so we can see what the electromagnetic predictions are from each phase in a more self-consistent way, so that we're not contaminated by initial conditions of the gas. And so this was kind of our proof of principle that we could do this. Eventually, you'll see these things merge. Let's see if I can jump ahead here. about to merge. All right, so then it forms a jet. So these were, our first simulations were on non-spinning black holes, all right? So then there was this jet that was formed because it formed a spinning black hole that could then launch a jet. So that was great. We used this handoff procedure that we developed actually for neutron star merger simulations, but then adapted to these new codes. The idea is that we take a spherical code that involves the CBD, the circumbinary disk, and then we hand it off to a code that can handle the merger process. So we want to relax the initial conditions, and then you can see the evolution of m dot, and this is the point of handoff, and you see that the accretion rate kind of follows a smooth trend, and we perform a number of tests to make sure that this is being done correctly. One kind of big finding that we found is that there was a prediction that, the binary, as it inspiraled and merged, it would actually accelerate and would peel away from the accreting mass. And so the accretion rate would drop, the mass available near the merger would drop, and there would be like no electromagnetic signal of the merger event. However, we actually found that the cavity region started filling up before the merger happened. So there was ample matter around to be, shocked against as the, gravitational potential changed, and that allowed, copious amounts of light to be liberated at the time of merger. We measured the variability of the signal leading up to merger, and we found, so there was this lump feature. This is a m=1 over density mode in the density that modulates the accretion onto the binary, and that modulates the light curve significantly. So this is twice the beat frequency between the binary orbital frequency and the orbital frequency of the lump. So it's a non-trivial dependence on the orbital frequency of the binary. This is the orbital frequency of the lump. So you can see how the lump kind of dominates the variability signatures in our outputs. There's this sloshing mass that goes, it's a mass between the mini disks that dissipates a significant amount of energy too. That is also not as much dominated by the beat mode, but operates more on the binary time scale. But doesn't show up as much in the light curve. So we then said, okay, what happens when we start off with black holes that spin? Well, you start off with jets, and these jets interact. They can be sites of reconnection, and that can also liberate more light. So this is a new way of maybe finding them, maybe in the radio, or maybe with high energy particles even. So we were able to find locations of reconnection sites, and that happens downstream, even out to 100 100 gravitational radii away. And comparing the evolution of various quantities between the non-spinning case and the spinning case, we see, for instance, if you focus on the EM aspect, so there's thermal emission that we predict from our simulations, and also kind of radio emission. Technically, this is the emission from the cooling function that we use, and this is emission from the Poynting flux that we record. And we find that the thermal emission does decay leading up to merger, but it doesn't decay as fast as the accretion rate does for the non-spinning case. That means that there's extra heating that happens right before merger. And also the Poynting flux in the non-spinning case increases over time, and that's probably because the black holes are moving faster as they inspiral. However, in the spinning case, you have a steadier thermal emission, light curve, but there are still significant enhancements at the time of merger. So if you're observing one of these systems and it suddenly brightens, that could be an indicator of a merger event. And we certainly see this in the Poynting flux. That is because you're forming a black hole with a larger spin. So we wanted to explore, well, okay, so we've been using this kind of ad hoc cooling function that's tied to the amount of entropy excess we have in the disk. Maybe this isn't the best way of modeling how radiation escapes that gas. So we tried out this method called the leakage method, which it uses the rate of diffusive radiative loss from the gas. So if you're in a very optically thick region, it takes a long time for that radiation to leak out. And so we model that radiative loss as such, where this F parameter is exponentially dependent on the optical depth of the fluid element. And so the diffusion timescale is just proportional to the optical depth and the scale height of that fluid element. So we devised this method, and we wanted to see how this affected the circumbinary disk evolution. And we started from initial conditions of using the legacy cooling function, let's say, that was connected to the entropy. And we then evolved that legacy run further, but then we started from a snapshot of the legacy run and used the leakage run from then on. And we found that we were able to find a good steady state in epoch 2 of the accretion flow, so m dot versus r. We saw more variability in the interior parts of the CBD, so more variability in the accretion rate, and also in the light curve. But the accretion rate remained about the same as in the legacy run. If you look at the surface density plot, you see the presence of that surface density peak that is characteristic in most of our simulations of CBDs, but that quickly erodes away. And what is happening here is that the disk gets thinner. It kind of compactifies the magnetic field. That increases the internal magnetic stress. That allows angular momentum to be distributed more efficiently, and it essentially erases the lump and the surface density peak. And you can see that the correlations between that the surface density local extrema are inversely correlated or anti-correlated with the magnetic field and the stress over time. So going back to the surface density, so these right columns, let's focus on the right columns. So the curves are the time evolutions of the legacy run, and the dashes are the time averages of the diffusion run, the leakage run. So you can compare the two more easily in these frames. So the surface density peak erodes the pressure, so the gas pressure per unit mass diminishes. The cooling time scale gets shorter, so it's cooling faster, more rapidly. And the aspect ratio, so it becomes a thinner disk. And you can see that this is a vertical slice through this. So what happens is that the magnetic field becomes more dominant, but it's also becomes dynamically dominant at the higher latitudes, so closer to the poles, whereas radiation pressure dominates closer to the equator. I want to spend a moment to advertise Katie's project. So this came out last year. So she used our ray tracing code to ray trace models of mini disks and how the black holes in a binary system lens the mini disk emission. So she used Jeremy's models for the flux from accretion onto spinning black holes that was found from GRMHD simulations, and she was able to ray trace these solutions and explore a vast parameter range of systems, exploring binary separations, inclination angles, time, spin, and one cool thing that she found was that, well, typically, when you ray trace a system, you fix everything in time, and then you let the photons go through them, through the space-time as if the light was traveling at infinite speed, and you ray trace just one snapshot of simulation data at a time. However, if you drop that condition, so we call that the fast light approximation. So if you drop that approximation and actually track the photons as the system is evolving, you actually see that the flares that you get they occur at different timescales, and that's because you have to take into consideration the launch time of those photons, and you can see that in the movie that it takes time for these photons to be launched from the background mini disk to arrive at the foreground black hole to be lensed and contribute to this flare. So this is a kind of a neat, novel prediction that these flares shouldn't be equidistant in time if you are in a binary. And this only occurs when you have a different mass ratio, too. So I just want to conclude here. And so this is an animation of the leakage run. So the legacy simulation is on the left, leakage run is on the right, and you don't see the lump anymore. So whether or not this is the case for all disks, this is one disk thickness, so maybe thinner disks have a lump or thicker disks have a lump. That's left to be seen, but for the parameters we used, which were like a million solar mass binary black hole system, we didn't see a lump. So that's going to affect the variability of the system. So, thanks.
Thanks for the great talk. I was wondering about your Inogi paper in which you're showing comparison between non-spinning and spinning. So some hydro simulations find that the X-ray signature disappear at the merger, then reappear back. Should I take from your simulation that it's not the case for spinning case, or it's not comparable?
I think in either case, there's going to be appreciable X-ray emission. We actually see that there are, as you get closer to the merger and also like right after merger, there are these shocks that occur in the cavity region. And those shocks are probably going to be able to produce a lot of high energy emission.
So in your case, it will not disappear?
I don't think it would disappear, no.
Okay. And just a clarification, what was the aspect ratio of the Inogi paper? This aspect ratio of the Inogi paper?
0.1.
So normally when we are looking into merger scenarios on the gravitational waves, much better that way. So I'm wondering, we have a condition for alerting the electromagnetic community a certain time before merger, provided we expect a high enough signal-to-noise ratio. These effects seem to happen way before merger, like, let's say, hundreds of orbits before merger, not just 10.
Yeah, no. Well, we showed you an evolution that was tens of orbits before merger.
Okay, so what I was really wondering was, should we look at the problem the other way around? Should the electromagnetic observations, should they happen, serendipitously, because we're not scanning the whole sky, as a prior for our mergers on the gravitational wave side?
Should we be looking for EM?
Yes, I mean, would that inform, for example, the data analysis for those mergers that do not have a humongous signal-to-noise ratio? I mean, if they have 1,000, who cares, right? We will tell you. If they have a signal-to-noise ratio of 10, right? But if you already know that they will be happening, right, because of these effects.
Yeah, no, I certainly hope. I mean, there are large sky surveys happening now that are searching for these things. I think they're focused on maybe more massive systems, but that's why we're doing this, is to actually give maybe alerts to Lisa, or suggestions. Maybe you should be analyzing the data, assuming there's a source over here. I hope that'll happen. So.
Okay, thanks, Scott. Next speaker is Michail from RIT.
Hi everyone. So today I'm going to present GRMHD simulations of massive black hole binaries. So we know that the black hole mass spectrum ranges 10 orders of magnitude, and in the recent years, LIGO and Virgo have successfully detected on the low mass sand mergers of low mass black holes. And on the high mass sand, we have detection of a gravitational wave background that is thought to be associated with a population of supermassive black hole binaries. Plus, we have observations of these objects, very high luminous objects that we call quasars in the high redshift universe. But in the near future, hopefully, Lisa will bridge this gap and detect black holes with mass in between 10 to the 4 and 10 to the 7 solar masses up to redshift 15. And all of Lisa sources will basically have potential electromagnetic emission. So with the current and future facilities, we will have like a bright future for multi-messenger astronomy. So the problem is that these electromagnetic searches, as we were saying, need models that have to be accurate enough to like support our understanding and interpretation. So these models have to be like accurate in order to like get the full physics and the ranges for the dynamical scales that goes from the kiloparsec to the subparsec scales when the gravitational wave emission takes over in the like history of the binary evolution. And this is very difficult, but there has been a lot of progress in this sense, trying to bridge these two, these enormous scales, and also trying to incorporate more sophisticated models, like for example going to larger separations where, for example, a post-Newtonian approximation for the binary space-time is still valid, or like trying to incorporate more accurate radiative transfer models, as we will hear, I think, later. But the more sophisticated is the model, the more like computationally expensive it becomes. So also, we know that if the energy and angular momentum of the binary is like emitted gradually, like during the in-spiral, for the linear momentum, like the emission of the linear momentum has this peak right a few orbits prior and then merger. And an isotropic emission of gravitational waves can lead to this asymmetric emission of net linear momentum or in parallel to the orbital plane, which imparts like a recoil to the remnant black hole, which receives a kick. And this kick is a function of the binary parameters, in particular the spin magnitude and orientation, and the binary mass ratio. And numerical relativity simulations are necessary to like accurate simulate this kind of problems. So recoiling massive black holes. And what they found is that these recoils can be pretty large when there is a significant contribution of the spin in the orbital plane. So for example, they found planar kicks up to 400 kilometers per second, super kicks where these spins are oppositely directed in the orbital plane up to 4,000 kilometers per second, and N-gap kicks where the spins are misaligned by 45 degrees with respect to the binary orbital angular momentum, up to, and we will come back to this later, up to 5,000 kilometers per second. And when these velocities are that high that they exceed the escape speeds of the galactic course, of course, there are important observational consequences because they can reduce the growth of merger remnants or like impact the merger rates. So in order we also know that these mergers, so massive black hole binary mergers, are thought to happen in gas-rich environments, and the typical gaseous configuration that is considered is a circumbinary disk that was presented earlier. So what they found is that a gap opens up at twice the binary orbital separation due to the gravitational torques exerted by the binary, but this cavity is not actually empty because there are streams coming from the circumbinary disk and from the N1 over density, the lump that forms at the CBD inner edge that modulate like the mass transfer and feed these mini disks that are visible on the left. This was for the spinning simulation by Enoji, and also these mini disks can also exchange mass in this process that we typically refer to as sloshing. So we heard earlier already that in order to produce astrophysically realistic data, we employ this end-off procedure. There is a three-step process. So we start from this circumbinary disk that is evolved. It's a magnetized, weakly magnetized torus in hydrostatic equilibrium. We evolve it for 165 orbits with a spherical coordinates code and a post-Newtonian approximation for the binary space-time. And then once we make sure that the system has reached a quasi-steady state, we can end it off the data to interpolate it and end it off to a Cartesian-based code, in this case, Illinois GRMHD, and we can proceed the evolution of the GRMHD simulation from the in-spiral up to merger and post-merger. So we use this setup to evolve the so-called N-gap kick simulation. So we try to broaden the parameter space, considering spins where they are misaligned with respect to the binary orbital angular momentum. In particular, the in-plane components have the same magnitude but opposite signs, and the out-of-plane components have the same magnitude and same signs. So this particular configuration combines the super kick and the N-gap effect, so maximizing the emission of net linear momentum and the kick. And this is a movie of the rest mass density in the equatorial XY, XZ, and YZ plane. And the separation that we start from is 20 gravitational radii or 20 m in code units, and the spin is 0.8, and they are equal mass. So to get like a closer view, these are snapshots of the rest mass density on top with insets of the cooling function in a zoom-in region, and then on the bottom is just the magnetization in the XZ plane. So we see how the gravito-magneto-torques, they divert the streams and they will tilt these mini disks. This is more evident in the 3D image on the left, but they are basically tilted by 45 degrees, so in the direction that is normal to the spin. And also, the jets that are produced due to the Blanford-Sonic effect, they are aligned with the spin axis, and this is evident in the bottom left panel from the magnetization. They will be aligned with the spin axis, but only up to this height of 5 m, and then they will reorient and align with the orbital angular momentum at larger distances, and eventually also merge into a single jet. And then on the middle panel is a snapshot right before merger. We see that the dual jet disappears as the mini disks also disappear because there's no more room, and because of the interplay between the yield sphere and disco. And there's also a magnetic gas that is emitted like in the form of flux tube that is evident in this particular snapshot. And on the right is the snapshot that is taken post-merger. So we see that a jet is actually relaunched and is highly magnetized and relativistic, and in particular, strong jets are emitted, and this is evident in the inset of the cooling function as well. So this movie is just to show better the merger and post-merger phase. So what happens is that due to the particular symmetries of the system, the black hole receives a recoil of more than 1,000 kilometers per second, and this is directed along the negative z. And because the outer bound radius that is theoretically predicted is an order of magnitude larger than our alpha edge of the computational grid, basically, all the disk will follow the black hole as expected. So it will move with the recoiling black hole. And we also, nevertheless, we are interested in what happens like closer in, because when we computed the luminosity by integrating the Coulomb rate over spheres of 15 and 100 M, for example, in the second panel, we see that the majority of the contribution comes from the inner regions, and so this is what we are interested in, and we also see the declining, as Scott was highlighting, and the deep and jump, and merger that is consistent with the spinning simulations. While the mass accretion rate in the third panel, for example, is more like declines overall, but then it settles onto this more constant value, like 1,000 M before merger, and then throughout the post-merger. And then if we focus on the post-merger part, we try to evolve it a little bit longer, and we see this interesting potential quasi-periodicity, where the maxima of like this kind of oscillations are associated with these shocks that persist throughout the post-merger and are associated with like dissipations of energy in the form of heat and magnetic energy. And finally, we could ask ourselves what happens to the lamp during this post-merger as the disk is following the black hole. And we see that from the space-time diagram of the M1 density mode, we see that the lamp established immediately, and it's forming between 2 and 3 times the binary separation with a strong, power, but also continues and is still present throughout the recoiling part and the merger, which is the dashed black line, and this is also evident in the linear scale plots. Of course, it's the amplitude is expected to decrease, but it still offers an important observational tracer for the dynamical history of the system. And then I can leave you with the conclusions. Thank you.
Got anything on? So I gotta share your mic. Sorry. So we know for the super kick, it has to be kind of like this, or the hang up with the 45-degree angle. But if it's out in phase when they merge, you don't always get the super kick. So is there a way to see in the gravitational wave signal whether or not the system got a super kick? So then we can somehow correlate that with the short-term EM signal.
So the super kick is the one where the spins are completely in the plane, oppositely directed. Are you referring to the super kick or the hang-up kick? Or both?
Either one, yeah. The one you were working on,
the hang-up. Yeah, I'm not sure, but you wanna know if there is a particular signature in the gravitational wave signal to find out if it's a recoiling black hole? Yeah, I'm not sure about that. There might be a memory effect.
You can ask Carlos.
Yes.
Thanks for the really interesting talk. I'm wondering if we can look for evidence of previously superkicked systems. So if we imagine that something has received a superkick in a merger and it brings the inner disk with it, then you should see systems, AGN, where there is no associated torus, right? You're kicking out the inner disk, right? It's being launched away, and there should be an offset between this sort of, the torus is no longer bound, it's going to diffuse outwards, right? There'll be some sort of dusty asymmetric outflow elsewhere, and there shouldn't be an infrared, or a strong infrared torus signal around the system. And so it'd be really interesting to sort of essentially put an upper limit on the number of systems that could have had a super kick, right?
Yeah, so as you see, the radius of the outer bound disk is like proportional to the velocity squared to the -2. So I think it depends on the velocity of the recoil. But there are a lot of like searches for like offset cores or like wakes that could like see, because in my case the disk like follows, and like so the most luminous part still follows the recoiling remnant, so maybe there's like some kind of trace.
All right. So thank you, Mariah Carey, again. The next speaker is Vishal Tiwari from Georgia Tech, still at Georgia Tech?
Defended last week.
Defended last week, doctor! You get an extra minute.
All right. So I'll be talking about radiation MHD simulations of these accretion flows around massive black hole binaries. And this work was done with the former postdoc who has left the field, Edwin, my advisor Tamara Bogdanovic, and collaborators Jan Fei-Xiang at CCA and Shane Davis, who's at University of Virginia. All right. Oops. Okay. So probably won't spend time on it because we know what the geometry of the gas around massive black holes looks like. But yeah, you have the mini disk, you have the circumbinary disk, there's streams coming from the CBD, which are feeding the neutral mini disk. And the problem is we need to find like these subparsec massive black hole binaries, which form in the aftermath of galaxy mergers, which will be at subparsec scale, so you cannot resolve them. So how do we find them and distinguish them between like regular AGNs? And that's the reason like we do simulations so that we can calculate these EM predictions because of the interaction of these gas with the binary. So here you're seeing all these amazing simulations that have been done in the literature, starting from like 2D hydro simulations where you have alpha viscosity. You can run them for like 10,000 binary orbits, ranging from like Newtonian MHD simulations to like a bunch of GRMHD simulations that you already heard about today. And then I'll be talking about like radiation MHD simulations. And you can see like as we include more and more physics, the cost of simulating per binary orbit increases. So the simulation I'll be talking about are not typically run on the orbit of 10 to even like 1 binary orbit. Okay, so because these RMHD simulations are so expensive, what we do is we divide the problem in two parts. We do the simulation for the circumbinary disk, where we cut out the mini disks, and that simulation is done by me. And the other simulation is we do the simulations for the mini disk, where we feed a stream from the outer boundary of the simulation domain. The stream self-intersects, form the mini disks, and those simulations are done by Edwin. So these are the properties at the bottom of the black holes that we're looking at. So the total mass is like 2 × 10⁷ solar masses, which are equal mass and a mass ratio of 10:1. So one black hole is 10 times massive than the other. They're circular, and they're separated by 100 gravitational radii. So definitely much farther away than the simulation that you saw previously. At the separation, they're orbiting each other at 7 days, and will be emitting gravitational waves, and will merge in
24 years or 74 years, depending on the mass ratio. And they'll be like Lisa precursors at this separation. Okay, so the code that we use is the radiator version of Athena++. So here's the physics that goes into the simulations. We use finite volume MHD, so you need magnetic fields so that you self-consistently transport angular momentum and have accretion onto the binary. We use Newtonian and post-Newtonian gravity, and we use like first principle opacities and full first principle radiative transport calculations, where you solve the full time-dependent transport equation for specific intensities and then couple them with the gas. So this is what goes into our simulations. Okay, so here, so to understand the effect of what radiation is doing to the circumbinary disk, we do two sets of simulations. So the first is RMHD, which includes radiation, and the other is MHD, which does not include radiation, and it's a locally isothermal equation of state for the gas, and it's 5/3 for the RMHD. So here, what you're looking at is the surface density, which is, you integrate the gas in the z direction. And what you can see is when you include radiation, the disk becomes much more filamentary as compared to the MHD disk. And the overdensity that a lot of other simulations notice in the MHD doesn't really stand out in the filamentary background of the RMHD. Then on the other side of the slide, what you're seeing is the azimuthally averaged density for MHD and RMHD. And you can see that when we include radiation, the disk becomes much more denser in the midplane and much more thinner. And this is because radiation can easily escape from the disk, which reduces the pressure support and kind of like collapses the disk. Okay. Oh, whoops, wasn't expecting that. Okay, so basically what you're looking at, because we have radiation in the simulation, we can calculate the light curves. So what you're looking at is we can put like hemispheres on top of the simulation and calculate the luminosity by integrating the radiation flux over these surfaces and get the luminosity and plot that versus time. And here is, okay, so the top panel is where you're looking at the light curves, and at the bottom you're looking at the PSD of those light curves. And what we find is the period associated with like half the binary orbit. This is because the inner edge of the disk becomes eccentric, and every time binary comes closer to the inner edge, it accretes gas. And the other, the power is at lower frequencies, which is associated with the inner edge of the circumbinary disk. Okay, because we have real opacity prescriptions, we can calculate or find the location of the photosphere. So here we are looking at radiation temperature, which is azimuthally averaged, and the solid lines are showing you the photosphere. So depending on what kind of a definition you use, people use like Rosalind or effective. In the literature, so we're showing those photospheres. At those photosphere locations, we can read off the radiation temperature because it's inbuilt into our simulation, and we can calculate the thermal spectrum from those radiation temperature, which you see on the other side. And you can see that massive black holes, which are separated by 100 Rg, accreting at 15% the Eddington rate, so the sub-Eddington disks will be emitting mostly in around optical UV band of the thermal spectrum. We can compare these results with like an alpha disk model where you can take a saccharosinide disk with the mass of like the same mass, same accretion rate, and cut it off like 200 Rg and calculate what it looks like. And we see that we underestimate the prediction that we get from the RMHD. And the other thing we can do is just use hydrodynamical quantities like the gas temperature and Thompson scattering. And if we use those quantities, we see that it overshoots because radiation and gas are not at the same temperatures. Okay. So what is the effect when we change the mass ratio? If you change the mass ratio from 0 equal mass to 10 to the 1, so the top one is showing the equal mass, the bottom one is showing the 0.1 case, and we can see that in the smaller mass ratio, because of weaker torques, the cavity becomes smaller, and also the overdensity is weaker in the 0.1 case. Okay. So how does it affect the observational properties of 0.1 versus the equal mass case? So here you're looking at the temperature at the photosphere. On the top is the 0.1 case, at the bottom is the equal mass case, and the solid line is showing the division between the optically thick and the optically thin regions. And you can see that because the cavity is smaller in the 0.1 case, the photosphere must deeper in, and also because the secondary is much closer to the inner edge and the photosphere, it can sample like much hotter gas. And because of that, the thermal spectrum that we get has much higher variability, which is the purple one. And the equal mass case doesn't have that variability. The peak spectrum is the same for both the simulations because they're the same disks. Okay, so I've been talking about the circumbinary disk. So what about the mini disk? So Edwin has done these simulations where he starts feeding a stream from the inner edge, and the stream self-intersects and forms these mini disks. One of the features that you see is in the mid-plane density slices with the MHD and RMHD that there's an overdense ring that forms at around 6 Rg. The characteristics are very similar. The RMHD disk becomes much more denser and filamentary. And here on the other side, you're looking at the colloidal slices at different phi value. And one of the things that you can see is the disk becomes very non-axisymmetric. And it has interesting consequences for the observational features of the disk. So what you're looking at, the first plot is showing the photosphere height, showing that the whole disk is very non-axisymmetric, that the region which is closer to the impact is like much more elevated than the other parts of the disk. And on the other side, you're looking at the temperature at the photosphere, basically. And you see that the mini disks are emitting at like the far UV at the temperature of 10 to the 5 Kelvin. One of the interesting feature because of this asymmetry is that you have radiation flux, which is highly non-axisymmetric. And because what you're looking at in this plot is basically the radiation flux, and you can see that if you look at a particular theta value, you can see that you have these variations as you go along the phi. So what does that mean for a binary? As you go around the binary, you will have this periodicity corresponding to this variation. Yeah, and I think I'm just gonna stop here, and if you have questions, let me know.
Thanks for the nice talk. I was wondering that. Thanks for the nice talk. I was wondering that, given that these simulations, all simulations, they depend on initial conditions.
Yeah.
So how and these orbits are very expensive to integrate. How do you make sure that before including radiation or magnetic field, your initial conditions are steady state, or how do you do it? Yeah.
So we start with a hydrostatic torus, and we self-consistently form an accretion disk from this torus. The simulations are in quasi-steady state, which means like they're still evolving, because to run these simulations, you need to like run them for like maybe hundreds, thousands of orbits. We have run for like 70 binary orbits, but yeah. So we need to make sure that we start with the better initial conditions, but the calculations we do here are like justified from like the inner part of the disk and the thermodynamical properties, which are self-consistently calculated.
So basically, before including radiation, you evolve the voltage.
Oh yeah, yes, right. So what we do is like we run an MHD simulation first, and then we turn on the radiation, basically. Save that computational cost on that. Yeah, that helps. I mean, I would like to run them for like very, very long, but we cannot do that. It's just too expensive.
Can you flip back to there was a slide that looked like it looked like magnetic field lines, but I don't think they were that. Yeah.
Oh, okay, yeah.
Are those radiation streams?
Yes.
Okay, can you talk about that a bit?
Yeah, so because we have radiation flux, it's in the code. It calculates from the specific intensities. You get the zeroth moment, you get radiation energy density. The second, you get radiation flux, and you can plot them as vectors. So you can see that it kind of like streams out from the disk and sorry, not from the disk, but from the photosphere, kind of. It's kind of difficult to see, but that's what it's showing here.
Yeah, because like we always just assume it comes out normal to the photosphere, but here it looks like it is coming out at a bit of an angle. Yeah. Okay, that'll be good. Maybe we'll talk about that. Anyone else? Okay, great. Let's thank Dr. Our next speaker is Jay from RIT. No, not RIT yet?
I moved to UIUC.
I'm like 5 years behind. Okay. Sorry.
So that's good. Alrighty. Hello, everyone. My name is Vijay Kalinani. I'm a postdoc at the University of Illinois, Urbana-Champaign. And firstly, I would like to thank the organizers for giving me this wonderful opportunity. And today I'll be talking about jet variability and small mass ratio supermassive binary black holes. This work has been done in collaboration with Manuela Campanelli, Michail Chabanov, and Maria Chiara di Simone, who you heard from earlier, Carlos Lusto, Helvi Vitek, and Josef Sachauer. Now, why do we care about small mass ratio SMBBH candidates? Apart from them being a promising LISA sources, these systems have very interesting electromagnetic signatures. For example, the famous OJ287 blazar is known to have a binary mass ratio about 1 to 100, showing these disk impact-like flares having a periodicity of about 12 years or so, and on larger scales, the jet that it powers has this very ribbon-like structures. And there's been a very nice attempt by Ressler, Combi et al. And Jiang et al. To model this system in fully generalistic magnetohydrodynamic simulations. That's what I show on right. And then there are other systems. The other one is J1048, which has a mass ratio of about 0.06 to 0.088, an orbital period of about 3.5 to 5 years, and known to have this flare periodicity of about 3 to 3.2 years. And on the right, you have the PKS to 2131. This is also well-known blazar, having a mass ratio not fully constrained, about 0.1 to 1, and orbital separation of about 0.001 to 0.01 parsecs, and flare periodicity of about 4.6 years. It is also shown to have this quiet period of about 19-20 years or so that you see in the middle of this plot on the right. Now, how do you explain these periodicities in the flares? Now, one model suggests, which is called the kinematic orbital model, proposed in Kilman et al., is that you have the jet nozzle that remains fixed, and the orbital motions essentially changes the velocity of the emitted material in the jet relative to the observer, and this is altering the Doppler boosting. And we have another model, which is a jet precession model, and here this suggests that the jet nozzle itself moves, and this is because the primary black hole spin is precessing. So this causes the periodicity in the observations. Now, in this work, we have performed a GRMHD simulation of a precessing supermassive binary black hole, having a mass ratio of 1 to 7, with the primary black hole, the larger one, having a spin which is oblique of minus 0.9, and the secondary, to keep things simple, we give it no spin. And we use the superimposed Kerr-Shield metric from Combi et al. And use the target entropy cooling that people talked about earlier. We start with an initial separation of 30 M, and we do this same game of running a circumbinary disk, and then we hand off this disk when the separation is about 25 M. That's what you see on the right. Now let's, so on the top left, you see now the spin components of how they evolve in time for the primary black hole. And interestingly, there is also a change in sign in the blue region where you have a flip of the black hole spin, the Z component. And similarly here, bottom left, you have the orbital angular momentum components. And here too, in the period where the simulation is evolved, in the blue region, what you see, there is also a flip of the orbital angular momentum of the binary. And on the right, what you see is the actual trajectories of the smaller black hole that almost starts perpendicular to the circumbinary disk, and then in time it becomes almost coplanar with the CBD. And here in our case, the primary black hole is also moving, unlike Combi et al., where they had the primary black hole fixed in the center. So let's look at what happens in the cavity. So this is on the time, the length scales of about 60 M, 16 Rg, however you want to call it. So on the left, you have the density evolution on the XY plane, and on the right, you have the density evolution in the XZ plane. So as you see that the secondary is so the main engine or the jet is driven by the primary black hole, and the secondary is acting like a perturber. And the accretion on the primary is very warped, as you see, like an S-like shape, for example, in this case. And what the secondary does is shocks the disk and pushes matter onto on the jet funnel. Let me see if I can fast forward this. Okay, let me see if I can do it here. Oh, well, we have to wait until kind of this ends. So you're stuck with the movie. So as you can see now, the jet itself is precessing, so you have a very tilted jet as well. And now the secondary is almost getting to be coplanar. So in this case, the accretion is continuously disrupted on the primary. And the secondary now also starts to form very temporary disks. And there's also sloshing that you can see on the XY plane. And this is, yes, so this is almost at the end. So let me just switch. But now let's see what happens in 3D, the same simulation. So you have, again, the primary in the center, it's moving, and you have a very warped, tilted accretion disk forming around this massive, the primary black hole. And because of this disk, you also have the magnetic field lines get warped around the disk, and in a toroidal way, so you start having magnetic winding, and this is also one of the ways you can actually launch a Blandford's night jet. And in time, you would see that the secondary that is now launching shocks, but also it sometimes gains or inherits these magnetic field lines. And as the orbit becomes more coplanar of the secondary, like I mentioned earlier, it starts to form these mini disks, or the disk, which are temporary, but also it leads to the depletion of accretion for the primary, and by the end of the simulation, you see barely any disk around the primary because of the secondary being coplanar. Now let's look at the accretion rate and the Poynting flux luminosity at the blackened horizon. So on top you see the initial part of the simulation where you have the secondary being almost vertical. You have these interesting disk impact spikes in the accretion, and then as it becomes more coplanar, the accretion rate for the secondary increases and becomes comparable with that of a primary. And the similar thing can be seen also in the Poynting flux luminosity, but the Poynting flux luminosity remains more or less much larger for the primary since it's also powering the jet. We also see high magnetization in the cavity. So for example, this is one instance where the magnetization became so high, it's of more than 10 to the power 3, or this, you have the accumulation of this fluxes, the vertical field lines, and these fluxes, the magnetic field is now pushed out from the system, and this can also be an efficient channel for tagging non-thermal variability in the system. Now, what happens on the much larger scale? So earlier I was talking about things happening inside the cavity of the order of 50, 60 M. Now, let's look 100 times larger. And here on the left you see the evolution of, on the meridional plane, top left is density, top right is Lorentz factor, bottom left is B square, and bottom right is temperature P over rho. You see that first the jet appears, and then you have these interesting shocks which look very periodic in nature. And second, this could be the quasi-periodic outflows that earlier was talked about. And then you also have the tilting of the jet. So essentially what you see is that the jet itself on large scale is precessing. And then it comes back to close to parallel to the Z orbit, the polar axis, and then temporarily the jet weakens. This is because the spin of the black hole, the primary black holes, switches. So it changes sign. And then the jet comes out again, and now it's bending on the other side, so it's the precession of the large-scale jet still continues, and you still have these shocks that form in time. And then later on, the jet starts to get weakened again. Now it's because of the secondary becoming coplanar and disrupting the accretion onto the primary. Now let's look at the top view of the Lorentz factor. This is a slice at z equals to 2500 m. So you see, along with the magnetic field lines, how the outflow is coming out from the system, and you have these swirling shocks that form, and then the magnetic field lines were rotating clockwise, and now the jet comes back again, and now the field lines are rotating counterclockwise. Now, looking at the Poynting flux luminosity at a distance, interestingly, we see there is a first drop because of the jet reorientation, because of the black hole flip, and then there is a second drop in because again of the accretion disruption because of the secondary becoming coplanar. Now, how do you form these shocks? Essentially, it's the secondary that's loading the funnel of the primary, which is now launched by the magnetic buoyancy in the system, in the magnetic tower, and then this material then becomes loop-like, and then that's pushed further down. Now, if we look at the maps of density on Lorentz factor, here you see on the x-axis is the time versus the z is the length scale along the z-axis. We see that these repeated diagonal bands that essentially show you these periodic shocks that form inside the jet. And looking at the periodicities of these things, so you have the m dot as well as the Poynting luminosity following a half-orbit period, whereas these upper and lower jet shocks are at a full orbit period. Finally, there was a recent paper by Thurnau et al. Showing that there are polarization swings in the OJ287 jet, and let's see what happens in our case too. So, due to the shocks that form in the jet, you also have these kinks that develop in the jet, and this can actually a promising scenario which can lead to these polarization swings as well. Now, let's put some numbers in our system. So skating to, for example, to PKS 2131, this was done with the help of Maria Chiara, taking the total mass of the system for about 8.5 times 10 to the power 9 solar masses, redshift of about 1.3 1.3, and again, the mass ratio is 1 to 7, we find that 1m is about 11.5 hours, and also equals to about 4 times 10 to the power 4 parsecs. So the period at 25m separation is about 2.3 years in observer frame. And when the shock cadence that I find at larger distances, about 1000 m, is about 4 years. Now comparing it to the PKS system 2131, the flare periodicity there is also roughly about 4.6 years. Now to conclude, the take-home message could be the primary black hole powers this precessing jet, and you have the secondary black hole causing these disk shocks that lead to jet shocks, and this could be another promising model to explain how you have these quasi-periodic outflows then that can lead to quasi-periodic oscillations. And we have jet weakening due to either the spin flip or due to the secondary becoming coplanar with the CBD, and this could explain, for example, the 1920-year quiet period in PKS 2131. We have flux tube eruptions and also jet shocks leading to kinks in the magnetic field, which causes these polarization shrinks. Let me stop here, and I'm happy to answer any questions. Thank you very much.
Any questions? Oh, Barry in the back.
That was excellent. Those movies are amazing. Just on the sort of jet spin, the spin flip and the changing of the jets, we observe systems where in some central galaxies we observe jets reorienting themselves. And so I wonder if, rather than ascribing that to, say, mergers that tilt the spin, is it possible that those systems reflect a binary that's formed and is tilting the jet in a new direction?
Yeah, I mean, that could possibly be. I'm not an expert, but these systems show that there can be spin flips, and that could lead to jet tilting, change of the polarization completely of the jet too. That can happen. I don't know if that answers your question.
What's the distance? So could you flip the direction of the jet significantly by, from one direction to like 70 degrees or 60 degrees offset by 40?
Oh yes, so the reorientation in this simulation happens at 180 degrees.
Right.
It's a complete flip. So first the jet is rotating like this, and then after the flip it's rotating the other way.
I see.
So that was also the magnetic field lines completely changed the polarization, the magnetic handedness. So it's by a complete 180-degree flip, and this happens on the time scales very quickly. Say, if you again talking about say thousands of 1000 m or so, that reorientation is pretty quick.
I see, but there's no. Sorry, I missed. So, is there a reorientation? Is there an angular change in the direction of the jet? Yeah, could yes. Effectively it be not 180? Yeah.
Yeah. It's a complete reorientation of the angle. Yeah. But in the sense that, of course, the jet remains in the large scale. There is also precession, right? So that angular change is already there as well, if that's what you mean. But yeah. Maybe I can talk later.
Okay, thank you.
Thank you.
And for our last speaker of the session, Tamara Bogdanovic from Georgia Tech.
Hello, everyone. It's great to be back to the International Visa Symposium, and it's great seeing you all again. Are we okay? Oh, we're still seeing. Let's try this again.
sharing the right screen. It's just not being mirrored onto the...
Yeah, it's showing the right on the webinar, but not...
Okay, so let's see if we can click the display. You're still good on Zoom? Okay.
Wow, I never saw them.
Okay, excellent. Let's get started. I would like to talk about the prospects for finding hosts of LISA's massive black hole binaries. So let me first start by recapping what we have hoped to learn from multi-messenger detections of massive black hole binaries. Well, for starters, we would like to learn about massive black hole formation and growth through either mergers or through accretion of gas. Of course, we would like to understand how massive black holes co-evolve with their host galaxies by understanding massive black holes through gravitational waves and by learning about the properties of their host galaxies from electromagnetic observations. And last but not the least, we would like to test our understanding of the cosmological model and our understanding of gravity in the strong field regime. And you will probably agree these are all novel goals, except there is one wrinkle in that plan. Merging massive black hole binaries have not yet been definitively detected in either gravitational waves or electromagnetically. So some important questions remain open. For example, if we hope to perform an electromagnetic follow-up of a merging massive black hole binary detected by LISA, should we expect the binary to be manifested as a luminous AGN, or should we merely be looking for light emitted by its host galaxy? And in that context, it's actually interesting to understand what are the prospects for detection of host galaxies to merging LISA binaries which are not active galactic nuclei. This exactly is the question that my graduate student, Kate Futrowski, is investigating. She could not be here today, so I will be talking about it. So our ability or chance to detect the host galaxy sensitively depends on the ability of gravitational wave detector to localize the gravitational wave source on the sky. And as an illustration of that scenario, I'm showing a sky map, gravitational wave sky map for a handful of LIGO, Virgo, Cagra sources here on the left, where you can see that sources are localized to relatively large regions on the sky that are shown like banana-shaped strips that you can see here on this sphere. And you may also see, if you squint, that these large regions have associated counterpart regions on the opposite side of the celestial sphere. So not only are these regions extended, they can be complex in shape, and they can be multimodal, which complicates the electromagnetic follow-up of gravitational wave sources. It does help to simplify that picture and to think about those uncertainties in the localization of gravitational wave sources as uncertainty on the sky, given by the uncertainty in the solid angle, as well as some measurement uncertainty in the luminosity distance given by delta DL. And this is exactly the way that we use to construct three-dimensional localization volumes for LISA where we envision that LISA has detected a massive black hole binary. The size of these sky localization volumes depend on many different parameters. On the binary's time to merger, the localization volume shrinks as the binary approaches merger. On the binary mass, its redshift, orbital configuration, orientation of the orbit on the sky, the spins of the two black holes, the location of the binary on the sky, and so on. And to calculate the size of the localization volume, we use the formalism developed by Manjali and collaborators to do so. And then Next, we want to understand how many galaxies are there inside of that localization volume. So to do that, we use a particular cosmological simulation called TNG100 from the illustrious The Next Generation simulation suite as our galaxy catalog. And the result of this exercise is shown here in this figure for a particular binary mass, 3 million solar masses, that is merging at redshift of 0.3. So what you see is the number of galaxies versus the time to merger, and I want you to only pay attention to this solid black line, which is showing you that 1 month before merger, the median number of galaxies that is enclosed in this volume is 700,000. I know. Followed by 4,600 1 day before merger, then 68 1 hour, and then less than 1 galaxy at the time of merger, which is shown in this little inset here. What does it mean, less than 1 galaxy, right? What does it mean to a theorist? It really means that the localization volume has shrunk so much that there is exactly 1 galaxy left inside of it, and that is the host to the binary merger. These blue strips basically show the number of galaxies enclosed in the volume of 68% of binaries, all of which have this mass and merge in this redshift, but have different spin configuration, different orbital configurations, locations on the sky, and so on. And the gray band, or rather green band, shows the 95th percentile. Now, if by some chance you can only select galaxies that host central black holes which have masses that are comparable to the mass of the binary detected by LISA, you can cut down the number of galaxies in this volume by a factor of 20 or 30, which is great. You have a way to cull that number. And the orange band here shows, again, the 68th percentile. The yellow band shows the associated 95th percentile of galaxies. But the take-home message that I want you to remember really is that good black hole mass estimators that would allow you to estimate the mass of the central massive black hole, or perhaps binary, will be key for early localization of binary host galaxies when there are many, many potential hosts in that volume. Moving on next. So from cosmological simulations, you can extract many possible demographic properties of galaxies, their mass, stellar mass, gas mass, but perhaps the most interesting one to discuss here is the brightness of galaxies that find themselves in the LISA localization volume. Again, considering the same binary mass, 3 million solar, merging at the same redshift, but now inside of a volume, localization volume as big as it is 3 days before coalescence. So again, you see the number of galaxies here as a function of their AB magnitude, where you see a number of lines here. These upper lines that are shown as solid lines show different photometric bands in SDSS, GRI-Z band, and then the reddest of all is the Roman F129 band. The key idea here being that if you're considering all galaxies in the volume, they tend to be very dim with magnitudes that are less bright than 28 magnitudes, so majority of them you wouldn't simply see with any survey. However, if you only select those galaxies with appropriate black hole masses, if you can make that estimate of the central black hole masses only select those that host black holes that have comparable mass to that of the binary, you actually recover a much different distribution of magnitudes that is shown with dashed lines that now peaks at magnitudes smaller than 24, meaning that host galaxies of LISA binaries are actually relatively bright, and many can be detected in surveys that are even shallower than 24 magnitudes. I should repeat here that in this case, we are agnostic about AGN emission from accreting massive black hole binaries and are only considering the light emitted by the host galaxy, okay? But it's interesting because these galaxies seem reasonably bright, at least at this redshift. Let's now look at that statement in a little bit more detail, considering the optical and near-infrared detectability of these galaxies. Again, the same scenario for the same binary and redshift. What I'm showing is, again, number of galaxies versus time to merger. And what I'm showing here on the top is actually the uncertainty in the localization on the sky as given by in degrees squared. So you can see that 1 month before merger, that size of that region is about 46 degrees squared, and it drops to about 1/10 of a degree 1 hour before merger, and it gets even less. So here, I only want you to focus on the bottom line here, the bottom blue line, which is basically saying that the Rubin Observatory should be able to see 10 to 71% of all galaxies that host massive black holes of appropriate mass. And this 10 to 71% depends on the exact band, photometric band, in which you're viewing them. And they should be detectable in a single pointing 1 week prior to merger, because this is when the Rubin's field of view encloses that localization region on the sky. And if you actually have 10 years of data to stack on that part of the sky, which we will have by the time that LISA flies, Rubin should be able to see 76 to 95% of these galaxies. Okay, moving on to actually do the same exercise for Roman. Roman should be able to see 27 to 64% of all galaxies with the appropriate central black hole masses within that mass cut in a single pointing 3 hours before merger, because this is when Roman's field of view encloses that localization region on the sky. And if you actually have a luxury of 1 hour exposure with Roman, Roman should be able to detect all galaxies within that mass range. So prospects for detection of host galaxies are actually quite promising. I will skip this slide in the interest of time. You can ask me about the X-ray detectability in the end if you're interested in. But in summary, I just wanted to say that host galaxies of LISA massive black hole binaries at redshift less than 1 are actually moderately massive. I didn't have time to discuss this. They're also gas-rich, but we can learn that. They're moderately bright in optical and near-infrared. And they're relatively dim in ultraviolet due to extinction and in 2 to 10 keV X-rays. So this is basically the flux range that we find in X-rays. The prospects for localization and detection of the host galaxies of such binaries at redshift, again, less than 1, are quite good in optical and near-infrared with Rubin and Roman. They are plausible. They're possible with lynx-like mission, which can peer really deeply in X-rays, but it requires very long exposure times. So perhaps a better use of lynx and new Athena-like missions is to search for any luminous AGN emission, if any, is associated with this merging massive black hole binaries, rather than to look for host galaxies. At redshift higher than 1, things become more challenging because there are a lot of galaxies in the localization volume, so good black hole mass estimators actually become key for selection of host galaxies because they allow us to cull down that huge sample of galaxies. And also, of course, characteristic AGN activity that may indicate the presence of a merging binary. I also wanted to say that if you would like to hear more about massive black hole binaries, you already heard a talk by Vishal Tiwari. Also go and see posters by my students, Tul Gautam, Julie Malevitz, and Sina Gobadi. Thank you very much.
Is that Tyson?
Hi, from way in the back. So one of the things that we're discussing, thinking about operations, is how often the follow-up community needs updates as these black holes approach merger, and the localization improves very quickly on very short timescales. So could you answer on behalf of the entire electromagnetic follow-up community, at what point is enough, and another update 15 minutes from now that shrinks the error localization region just a little bit just isn't worth your time? You're already planning the follow-up observations.
Okay, so let me sink in all the answers from the entire electromagnetic community. So thank you, that's a very good question. And like every good question, the answer is it depends, I would say. What does it depend on? It depends on how fast is the evolution of the localization volume in these final stages before merger. If it's evolving really quickly, you may want to let the electromagnetic community know. They don't have to search this big of a region on the sky. Instead of that, a region that is 5 times smaller, that would definitely help. I think that that's particularly true towards the end of the evolution, or closer to the merger, that evolution will be rapid. So the answer that you probably don't want to hear is as often as possible, but it is a qualitative answer that I will give. I think that what sets the cadence of updates is definitely a question that should be considered more carefully. And it depends on the time it required to slew the telescopes. It depends on the time, on the rate of evolution of different parameters, how much better are they constrained after some certain amount of time, and so on. So, not a simple answer, but it actually may be a different answer for different systems, is I guess what I'm saying.
Thanks. Right behind you, Shane.
Hi, thank you for a really interesting talk. I have a question about the black hole mass, galaxy mass relations you might be using, and how good are those models for binaries and galaxy merger sites, and what kind of improvements do you need to do higher redshift localization when galaxy morphologies and that black hole mass relation is not as well known?
So actually, there is no black hole mass host galaxy scaling relationship that was explicitly used in this exercise. But there is one that is implicitly built in cosmological simulations, and it's as realistic as the modeling of different effects in cosmological simulations is. So that is my answer to this part of the question. Obviously, if you want to have a good mass estimators, which is something that I mentioned will be crucial to early localization of host galaxies, they will rely heavily on scaling relationships. So I guess my pitch here to the electromagnetic survey communities is that it would be great as auxiliary data to have estimates for central massive black holes, masses of central massive black holes in galaxies, and to those who are calibrating scaling relationships, they would be great to understand them even better and to a higher redshift, so that we can basically play this game and eliminate hopefully a large number of host candidates from our list, so that we can focus only on galaxies that matter.
All right, let's thank the speaker again. Unless there are any last-minute announcements from the organizers, it's just run and grab your coffee and try to get back by 4 o'clock.